So we are going to derive the Euler-Lagrange equation. So the idea is that the path x of t that extremizes S satisfies the Euler-Lagrange equation and that equation is the partial derivative of the Lagrangian with respect to x minus d by dt of the partial derivative of L with respect to x dot equals to 0. Okay, so we are going to prove this. We're going to prove this starting from the principle of least action. So we assume that our Lagrangian is only depends on x of t and its first derivative. Okay, no higher derivative. We are not assuming higher derivatives because physics usually doesn't require those sort of Lagrangians. Okay. So now, as we vary x, so x goes to x plus delta of x, then the action S changes to S plus delta of S. What is this thing? This is integral from t0 to tf d of t, and then the action L, so the Lagrangian L, but now instead of x, you have x plus delta x. Instead of x dot, you have x dot plus delta x dot. Okay? And so then what we can do is that we can just use the fact that the Lagrangian only depends on x and x dot to express this as the Lagrangian at x dot plus the change of the Lagrangian with respect to x delta of x plus the change of the Lagrangian with respect to x dot delta of x dot. We are doing a Taylor expansion. So the first term is nothing but S. So we can write delta of S to be the other two terms. So delta of S is going to be the integral from t0 to tf d of t, the partial derivative of L with respect to x, delta of x plus the partial derivative of L with respect to x dot, delta of x dot. Now I'm going to use something which I'll prove afterwards, is that if I take delta x and its time derivative, that's the same thing as taking the variation of x dot. Okay? In other words, the variation and time derivative commute. So I'm going to use that. So now what I can do is that the first term, I'm going to see that this has delta x dot, but I want to have a term, all terms which has delta x in it. So I'm going to do an integration by parts for this term. So delta of S is t0 to tf d of t. The first terms remain the same, delta t, delta L, delta x. The second term, we get a total derivative with respect to time, delta L by delta x. And here I'm using the fact that the time derivative can be pulled out of the variation. minus d by dt acting on delta L. So there's a dot here, times delta x. So we have two terms which have delta x and one term which has delta x but is a total derivative. Now we can re-express this term and write the total derivative. We can do the integral in the total derivative term, and then the total derivative term becomes delta L by delta x dot times delta x, with the boundaries being t0 and tf. But we know that delta x at these boundaries vanish. So this term is going to be 0. So we are left with plus integral from t0 to tf, this term, dt. What is this term? Delta L by delta x. Delta L by delta x, and then this term, which is minus d by dt, delta L by delta x dot, and I'm factoring out the delta x from both of these terms. Now, according to the principle of least action for the physical path, delta s is 0. That means that this thing is 0. But you see that this variation is arbitrary. It's a function of chi. It's small, but it's arbitrary. That means that if this is to be true, then the integrand has to be true identically. And therefore, since delta x is small but arbitrary, this means that the integrand is identically 0, which means that delta L by delta x minus d by dt, delta L by delta x dot is 0. And this is the Euler-Lagrange equation, okay? If you're a physicist, you will need this equation for the rest of your life.